This is our group member.
Our group will discuss two topics from Math 2, which is logic and proof. Logic is branch of mathematics that studies proposition, truth value, and logical reasoning. Logic allows to analyze statements and determine whether they are true or false. Second, proof is mathematical statement is an expression which is either true and false. A mathematical proof is convincing argument which express the language of mathematics. Alright, we go to logic first. In logic, we have proposition. Proposition is a declarative sentence that has definite truth value, either true or false. And we have two types of proposition. First, primitive proposition, statement that are free from logical operator. Second, we have compound proposition, statement that has at least one logical operator. And let's take a look at picture on the bottom slide. First picture, we have five logical operator: negation, and, or, implies, and biconditional. Next picture, we have four statement condition. First, condition statement. Second, converse statement. Third, inverse statement. Lastly, contrapositive statement. Right, we go to example 1. We have given statement: if a number is divisible by 5, then the number ends with 0 or 5. Let's divide the statement to P and Q. P, a number is divisible by 5. Q, the number ends with 0 or 5. This statement is written as P implies Q. Firstly, if we want to do a converse statement, the statement is written as Q implies P. So, the statement be, if a number ends with 0 or 5, then the number is divisible by 5. Secondly, if we want to do an inverse statement, the statement is written as negation P implies negation Q. So, the statement is, if a number is not divisible by 5, then the number does not end with 0 or 5. Thirdly, if we want to do a contrapositive statement, the statement is written as negation Q implies negation P. So, the statement be, if a number does not end with 0 or 5, then the number is not divisible by 5.
Okay, now we talk about the laws of logic. As shown in the table, there are exactly 10 laws: identity laws, never negation laws, idempotent laws, and so on. And then we talk about rules of inference. First, modus tollens. If P implies Q, then and Q is false, then P must also be false. Modus ponens, if P implies Q and P is true, then Q must be true. Simplification, if P and Q is true, then P is true and Q is also true. And then conjunction, if P is true and Q is true, then P and Q is true. And then disjunctive syllogism, if P or Q is true and P is false, then Q must be true. And then addition, or we call disjunctive amplification, if P is true, then P or Q is also true. Lastly, hypothetical syllogism, if P implies Q and Q implies R, then P implies R. Okay, now we move on for example 2. For example 2, we are asked to simplify a logical expression using the laws of logic. The given expression is negation P or Q, close bracket, and P. First, we apply De Morgan's law, which states that negation P or Q is equivalent to negation P and negation Q. So the expression becomes bracket, negation P and negation Q, close bracket, and P. Next, we rearrange the terms using the associative and commutative laws. This gives us bracket, negation P and P, close bracket, and negation Q. Now we apply the complement law where negation P and P equals false. So the expression becomes false and negation Q. Finally, using the identity law, false and anything is false. Therefore, the simplified result is false. And now we move on to example 3. For example 3, I will explain the proof step by step using the rules of inference. Step 1. First, we define all the statements P, Q, R, S, and T. Next, we list all the given premises. These premises are assumed to be true at the start of the proof. From 1 and 2, we use law of syllogism, which states P implies negation R. And then from 3, we use commutative law, R or S. And then from 7, we use equivalence identity because negation R implies S. From 6 and 8, we use law of syllogism because P implies S. And then from 4, we use equivalence identity because S implies T. And then from 9 and 10, we use law of syllogism which states that P implies T. And then we got the conclusion using 5 and 11, we use modus tollens, we got negation P.
So if you guys wanna know, in proof, there are 7 proving techniques. There are the forward-backward method, the construction method, the choose method, specialization, the contradiction, contrapositive, mathematical induction. But in our group, we will discuss just 3 techniques. There are the forward-backward method, the choosing method, and specialization.
This slide, I will explain the forward-backward method, which is commonly used in mathematical proof. In this method, we are given 2 statements, where it is statement A is the hypothesis and the statement B is the conclusion. If we want to prove that statement A implies statement B, we start by assuming that A is true. Then, using logical step, we show that B must also be true. This process is known as the forward process because we move forward from the hypothesis to the conclusion. However, in some cases, it is easier to understand the proof by starting from the conclusion. To do this, we assume that statement B is true and work backward to reach statement A. This is called the backward process, and it helps us to see how the conclusion is connected to the hypothesis. The choice between forward or backward method depends on the information given in the question. Usually, when the statement contains a universal quantifier like for all, the backward method is often more suitable. In summary, the forward-backward method helps us to prove a statement clearly by connecting the hypothesis and the conclusion in a logical way. Okay, next, for this slide, show an example of the forward process and backward process. We are given a right triangle XYZ with side of length x and y and a hypotenuse of length z. The hypothesis A states that the area of triangle XYZ is z squared over 4. The conclusion B is that right triangle XYZ is isosceles. First, we consider the forward process. From the hypothesis, area of XYZ equals z squared over 4 using the area formula of a right triangle. 1/2 xy equals z squared over 4. Next, using the Pythagoras theorem, z squared equal to x squared plus y squared. And then we substitute z squared into the equation and simplify. This gives a bracket x minus y squared equals 0 which is implies S equal to Y. Therefore, B is established. So, if A then B or A implies B, next we look at the backward process. We start from the conclusion, where it is B x equal to Y. This gives in bracket x minus y square equal to 0. By rearranging, we obtain z square equal to 2xy. Substituting this into the area formula, we get area of xyz equal to z square over 4. Therefore, A is established and the proof is complete.
So now we move on to the chosen method. The statement in backward process contain universal quantities like for all. The step is identify the statement. Second, use backward process. Third is use forward until backward and forward equivalent. For example, given two set S and T defined as follow. S equal to bracket real number x square negative 1 less than or equal to 0, and T equal to bracket real number x negative 1 less than or equal to x less than or equal to 1. Use the choose method to prove that T subset S. Your answer should have an analysis of proof and the considered proof.
So for the step A, set S equal to bracket real number x square minus 1 less than 0, and set T real number x minus 1 less than or equal to x less than or equal to 1. For set B, set T subset set S. For set B1, for all element T in set T is in set S. For set A1, choose an element say T in set T. For set B2, T1 is in set S. For set B3, T1 square minus 1 less than 0. For set A2, negative 1 less than or equal to T1 less than or equal to 1. For set A3, T1 greater than or equal to negative 1 and T1 less than or equal to 1. For set A4, bracket T1 plus 1 and minus T1 less than 0. For set A5, bracket T1 plus 1 times T1 minus 1 less than or equal to 0. For A6, negative T1 square minus 1 less than 0. So that set A equivalent to set B3.
Okay, right now for specialization method. When we use the specialization method, we use specialization method if an hypothesis contains quantifier for all, denoted as for all. And for the steps, first assume that A is true and identify the object contained properly and something happened. For the second step, look for first particular object to apply specialization method. It's often this object is out and from the backward process. And for the third step, verify that this particular object does have certain properly specified in A, that is for all. And for the last step, conclude by a new statement in the forward process that the something happened for this specialization method. Okay. Alright, right now for example 1 for this topic. For set R, S and T, prove by specialization method that if R subset S and S subset T, then R subset T. Your answer should have an analysis of proof A. Okay, where A, we are given that R subset S and S subset T. B, our goal is to prove that R subset T. Next, B1, to prove R subset T, we must show that for all of the set, R subset R and R also subset T. A1, choose an arbitrary element R prime, element R. For B2, we want to show that this element R prime that show that element T. For N2, since R subset S, by definition of subset, for all R subset R, we have R subset S. And for A3, since S subset T, by definition of subset, for all S subset by set S, we have S subset T. Specializing A2 to R prime, which is in R from A1. For A4, R prime subset to set S, using A3 and fact that R prime is set by set S. A5, R prime element of T, so A5 is equivalent to B2. This shows exactly what we want in B2, that the chosen element R prime is in T. So, okay, lastly, to conclude our presentation for chapter 2, in this chapter, we know how to change given statement to converse, inverse, and contrapositive statement. We know how ideas connect through implication. We know how some statements are secretly twins with logical equivalent. We know how the laws of logic and the rules of inference help us move from one problem to another smoothly. For chapter 3, in conclusion, proof help us show that a statement is correct using clear steps. The forward method starts from given information and moves step by step to the result. The backward method starts from what we want to prove and works backward. The choose method is used by selecting an example that fits the condition, while specialization method focuses on specific cause to make proving easier. Overall, this method helps us explain ideas clearly, logically in mathematics.